Hi folks, Astronomy Live here. A month ago I created this video identifying the bright planet in the southwest sky after sunset as the planet Venus. I performed astrometry of its coordinates and compared it to calculations based on the orbit of Venus as published back in the 19th century. The video has gone viral and currently has over 63,000 views and is still climbing despite the fact that it was uploaded a month ago. That's quite a lot more than most of my videos get, and likewise, a live webcast that I did last week of Venus through the telescope has over 11,000 views and is climbing, and that's quite a lot more than most of my live webcasts get as well. So a lot of people are interested in this subject, and a lot of people wish to identify this object, and the most common question that I get in response to these videos asks why it is so bright. People don't remember it ever being this bright. They think there might be something abnormal about it, or that it might not really be Venus, because they don't ever recall seeing it this bright before. So in this video I'm going to address the brightness of Venus, and we're going to find out whether or not it's brighter than it has been in the past, and whether it's really as bright as it should be, based on historic data and equations that are, quite frankly, older than most people who are watching this video right now. So let's take a look and see what we can find out. So to start off, here is an image I took last night of Venus next to the crescent moon. You can see a bit of Earth shine in the darkened portion of the moon, and you can see that Venus is quite bright, but the question is whether it's brighter than it should be, or brighter than it has been in the past. To answer this question, we use a technique called photometry. Photometry is the measurement of the brightness of astronomical objects, and you can do it a number of ways, but one popular modern way is to use a CCD camera and to measure the brightness of the object compared to other objects in the field of view. In this case, we'll use the moon as a reference for how bright Venus is. So I've created a drop canvas here that has a number of documents. We have the image in JPEG format, the image in a raw FITS file, which is what the photometry was actually performed on, and some screenshots of the software that performed the photometry. But we need to know how bright Venus is expected to be based on historical data. So to get historic data on how bright Venus should be, I'm going to refer to this book, The Solar System, Volume 3, Planets and Satellites, originally published in 1961. You can find this book in a wide variety of university libraries. I've looked at it in those libraries, and the scan that I'm going to refer to in this video is legitimate. The numbers are the same as what you will find in the physical copies of the book. And within this book, you'll see equations for how to calculate the brightness of the planets, including Venus. And to start off, we have to take a look here at the general equation for how to calculate the brightness of a given planet. You have an absolute magnitude, designated here as V1, 0, plus 5 times the log of the distance of the planet from the Earth times the distance of the planet from the Sun in astronomical units, plus delta MA, which is a phase angle function. So in this case, Venus's phase is decreasing day by day, but its distance is also decreasing. And because of this, these competing factors actually cause Venus to continue to get brighter, even though its phase is getting smaller every day. And this is because its distance to Earth is also decreasing. And for a period of time, that is actually the dominant effect. If you run the numbers, you'll see this. And in the video description, you'll find a spreadsheet that has these equations already put into it, and you can change the date and see how the brightness of Venus is expected to continue to increase as it gets closer to Earth. Keep in mind that in astronomy, the magnitude scale is such that the smaller the number, the brighter the object, or in the case of Venus, the more negative the number, the brighter Venus is. Now, in the next page, you will find the equation for the phase angle function of Venus. This varies depending on the object, and the equation is given here based on data that was actually collected in the 1930s to early 1940s, and finally published in 1949. And this continues to work quite well even today. The letter A denotes the phase angle of Venus, and when you plug that in and add it into this equation along with the absolute magnitude of Venus given as about negative 4.29, you'll find the expected apparent magnitude of Venus. Now we want to also know the expected apparent magnitude of the Moon, because that will be our reference for the image that I just showed you. So if we go forward a few pages, we'll find similar data for the Moon, and we have a phase angle equation here for the Moon. This is based off of photoelectric data collected again in the 1930s. So, you know, these data and these equations really predate most people who are probably even watching this video. So if we plug these numbers in, we can calculate what the expected magnitude of the Moon and Venus were supposed to be at the time of observation, which was on the evening of January 1st, which was actually January 2nd by Universal Time. And you can see that the apparent magnitude of the Moon should have been about negative 7.825, and the apparent magnitude of Venus should have been about negative 4.239. So now we need to calculate how bright it actually was in the image. So if we come back to the image and put it into AstroImageJ, you'll see that we can actually measure the integrated brightness of the object within the image, and it's up here in this top field, INTCNTS. This is the integrated brightness of the object in the innermost circle. And in the case of Venus, the number is about 1.8 million. And this is an arbitrary number, but it will become the apparent magnitude when we plug it into a final equation for calculating it based on the brightness of the Moon in the image. And so if we measure the intensity of the Moon in the image, we find that its intensity was about 50 million and change. And so we can take these two numbers, the integrated brightness of the Moon and Venus, and put them into a pretty simple formula to calculate what the apparent magnitude of Venus is in this image. And I've got a second spreadsheet here that calculates that. That will also be in the drop canvas link in the video description. It's simply negative 2.5 times the log of the intensity of the unknown divided by the intensity of the known plus the magnitude of the known object. In this case, the known object is the Moon and the unknown object is Venus. So if we plug in the intensity numbers we have from AstroImageJ and the apparent magnitude of the Moon as calculated by the spreadsheet, we end up with an apparent magnitude of Venus in the image of about negative 4.22, which is right in line with what we expect. It's surprising to most people and counterintuitive, but Venus actually reaches its brightest point when it's a crescent phase, because its proximity to Earth is the dominant factor in determining how bright it is, until that phase becomes very, very small and the crescent becomes very thin as it approaches the Sun in the sky. But until that point, the closing distance between Venus and Earth will cause it to continue to get brighter. So right now, its apparent magnitude is expected to be about negative 4.239. But if we go forward 1 month, we find out that the magnitude is expected to decrease even more, meaning it actually is expected to get even brighter with an apparent magnitude of about negative 4.45 and change. So this is expected because it's getting closer to Earth, and that's what it should be doing based on its orbit. So I hope that answers your questions. I'll put the link to this spreadsheet along with the other spreadsheet in the video description, along with links to the pictures used in this video. Thanks for watching. Clear skies, folks.